Thank you very much for the introduction. I'd like to talk today about DGeometrica. And this is a mathematical package to compute and visualize differential geometrical objects in the classical theory of curves and surfaces. And it is an educational package. I mean, a package supposed to be used in a class of differential geometry to help students understand geometrical objects. And of course, there is a package titled Geometrica, created by Professor Bruno Outan about Euclidean geometry. But my package has a capital D here to indicate differential geometry. At the previous IMS 2001 in Avignon, I introduced the first half of the Geometrica about plane curves and space curves. And this time, I will mainly introduce the second half about surfaces. And all commands in the Geometrica are now converted to version 6 of Mathematica. And in this 15-minute talk, I'd like to sketch the outline of the Geometrica, and I'll demonstrate the features in more details in the workshop that follows this talk. About differential geometry and Mathematica, there's a nice book written by Alfred Gray, this one, Modern Differential Geometry of Curves and Surfaces with Mathematica. And its first edition was published in 1993, and I was impressed by his book very much, especially by his use of the Mathematica command ndsolve to obtain space curves with assigned curvature and torsion. And I tried to use the Geometrica myself to visualize one of my surfaces. And my surface is contained in the two-dimensional complex space, that is the four-dimensional real space. And I defined the surface by means of a solution of a differential equation and guaranteed its existence by the existence and uniqueness theorem for differential equations. And I didn't know the, explicit expression of this surface, nor its shape. I just imagined the shape in my mind, but Mathematica solved the differential equations numerically and drew these pictures. Actually, these are pictures of the surface projected to four different three-dimensional spaces. And this is very close to my image in my mind, and I realized the power of Mathematica through these pictures, and this was the beginning of my use of Mathematica in differential geometry. And I published a book, this book, in 1999, and this book was written in Japanese language, and the present DGeometrica is a Mathematica package consisting mainly of the topics contained in this book. So I'd like to explain the features of my book, namely the features of DGeometrica compared to the book of Alfred Gray. First, I put more stress on experimental approach, making use of various numerical functions of Mathematica, such as ndsolve or nintegrate. And this makes us possible to extend the range of examples tremendously, and even to do some kind of experiments in differential geometry. And secondly, I put stress on visualization of the objects that appear in differential geometry through animations, making use of various graphics functions of Mathematica. And these graphics functions are improved very much in the version 6. And thirdly, there are about 80 commands contained in this DGeometrica, and most of them are designed for general use. Not only to obtain a single result, but rather to obtain generic results by changing the curve's surfaces or parameters, just like the default functions of Mathematica. Of course, this is possible through symbolic computation of Mathematica. And in the following, I'd like to explain these features through examples. The examples in differential geometry had been traditionally confined to a small group of calculable objects. This is mainly because the integration, or more generally, solutions of differential equations that appear in differential geometry are beyond our hand calculation, except for very simple curves or surfaces. But numerical functions of Mathematica makes it possible to do, to treat curves or surfaces if just it's the parameterization is given, even if the parameterization is fairly complicated. So this makes the range of examples make very wide, and even to treat randomly generated curves or surfaces. This command generates a plane closed curve randomly. First, we open the package by entering this command, and then we can obtain the usage explanation like this. And entering this command in this way, we obtain this output. Actually, this is not a real-time output. All commands in this talk are input in advance to save time. And this is a randomly generated closed curve, and this is its parameterization. Every time we enter this command, we obtain different curves. Since they come with this parameterization, we can treat them differential geometrically through making use of Mathematica. The next example is about homotopy. Homotopy is a continuous deformation of curves or surfaces. So we give two curves, this one and this one. Actually, the first one is one of the randomly generated curve, and the second one is the unit circle with negative orientation. And we use this command in this way, then we obtain this output. Maybe the size of the, too large, but yeah. This is the randomly generated closed curve, and this red circle shows the image of the so-called Gauss map, and this indicates the rotation number of this curve. At this moment, it is -2. And the rotation number is calculated by the integration of the curvature function. And this one shows the so-called, the total absolute curvature. It is defined by the integration of the absolute value of the curvature. And in this figure, it is shown divided by 2 times pi. And we consider a homotopy from this curve to the unit circle with negative orientation like this. And there is a well-known theorem by Fenchel that the total absolute curvature is greater than or equal to 2 times pi, and it is equal to 2 times pi if and only if the curve is convex. And we can verify the statement through this animation. I'll say. From this point of the homotopy parameter, the total absolute curvature divided by 2 times pi is equal to 1, and the homotopy curve is convex. So we may say this animation is a kind of experiment to verify the statement of Fenchel's theorem. And since this command is designed for general use, we can change the curves and obtain different animations like this. Oops. I have to stop this one and show the next one like this. And actually, we can observe, how to say, a catastrophe here. A catastrophe is the discontinuity of the phenomena in the sense of Ronet tone. Here, we have some kind of catastrophe. Next examples are about geodesics. And geodesic is, how to say, a curve on a surface, locally the shortest curve connecting the 2 points on the curve. And we use here the ND solve to solve the differential equation of geodesics. This example shows geodesics on a torus by fixing the initial point here and changing the initial direction. The next example is also about the geodesics on torus. By fixing the initial point and initial direction and changing the length of the geodesic. We can manipulate the opacity through this button like this, transparent, and half transparent and not transparent. So this makes clear the curves on surfaces. This is a very nice feature of the Mathematica version 6. And as a conclusion, I'd like to say a few words about what I'm trying to do after DGeometrica. Before that, I'll show the last example, this one. This is about the so-called geodesic coordinate. Geodesic coordinate is a coordinate system whose coordinate curves consist of geodesics and geodesic circles. The red curves are geodesics and the blue curves are geodesic circles. So, of course, I'm using the numerical functions of Mathematica completely. And as a conclusion, I'd like to mention a few words about what I'm trying to do after DGeometrica. The first one is visualization of the proofs of theorems. For example, the visualization of the proofs of proof of Gauss-Bonnet theorem. And actually, I presented partially about it in the IMS 2001. And the second one is the package for tensor calculation in differential geometry. And this is this is related very much to the talk of Professor Baller this morning. And the third one is about the curves and surfaces in higher dimensional spaces. I have just an example here. Yeah, I'd like to show one example. I put a link here, but it disappears, so I have to find it. This is a surface contained in the two-dimensional complex space, that is the four-dimensional real space. And the animation is obtained by rotating the surface in the four-dimensional space and then projecting it to the three-dimensional space. It looks as if the surface is changing its shape, but in the four-dimensional space, it is a solid shape, just rotating itself. I showed this animation in the International Congress on Differential Geometry in memory of Professor Alfred Gray, which was held in Bilbao in the year 2000 in Spain. So I'd like to, I wish I could report on these topics in the future IMS. This is all for the talk, and if you are interested in, please join the workshop that follows this talk. Thank you very much for your attention.
At this point, do we have questions? Or do we save these questions to the end?
You, in the beginning, you mentioned that you have written your package for education.
Yes.
Yeah. So I would like to know how the students react to your Mathematica kind of. I mean, I can relate to all of this and to quotation numbers and whatever. But how do students like your geometry?
Yeah, sometimes in the education of mathematics, some teachers put more stress on logical parts of the mathematics. But the most important thing is a kind of, how to say, intuition, or how to say, I don't have precise expression in English, but the image in brain, that how to construct image in the brains of students. So this kind of animation is a very nice tool to get some image of the concepts about differential geometry or any subject.
At least for the imaging to get the idea how things supposed to work, I guess that helps them out. At least in my experience, I had to teach quantum mechanics, and initially teaching or exposing the students to Mathematica, I got two fractions of the students, one who liked Mathematica more than quantum mechanics, and those who liked quantum mechanics more than Mathematica, and they split it away. Any other questions? Okay, then I'd say we simply go on with the workshop.
Okay.
And don't waste any more time, because I'm not sure if we get kicked out at 6. I hope we don't, but we should have 3 more minutes.
Yeah, 3 more
Okay,
minutes.
you're welcome to join and stay here. The computer, sorry, they should be connected by Wi-Fi. So